Today we have Matthew Taylor with us. He's going to talk about reinforcement learning in the real world, and he's coming from University of Alberta. He's a professor there. He's also a member of the AMI Institute, together with quite a few other extremely good reinforcement learning researchers. And we are very excited about hearing about his work because, as I was saying a few moments ago, we recently started having more interest in human-assisted modeling or interaction between humans and machine learning modeling. And Matthew is one of the few experts, at least according to our survey of the field. There's not that much of a high-quality research going on, and Matthew seems to be one of the leaders in that domain. So we're very happy to have him here. Without further ado, please go ahead.
Great, thanks for the introduction. Very, very nice way of saying I'm a large fish in a small pond. I like that. Not a lot of people are working in this area, but more people should be. So what I'd like, oh, sorry, before I jumped into the actual content, not everyone knows that U of A is ranked a top 10 university for AI and machine learning. And in Edmonton, if you ever get a chance to come, in addition to U of A, there's Alta ML, there's a DeepMind lab, there's Huawei. So Edmonton is actually a pretty fun place. If you come on the wrong day in winter, it does get down to -40, just FYI. Summers are amazing. I did want to mention AMI briefly, because again, outside of Canada, not everyone's heard about it. It's part of the pan-Canadian strategy. So there's Mila, Vector, and AMI, and the federal government put in over $100 million into funding these 3 AI labs. So it's great. I'm surrounded by just amazing professors. It's so much fun to have so many RL people around me. And AMI, the nonprofit, works on like upskilling, trying to find business opportunities, partnering with companies, that kind of thing. So just something I wanted to let you know is out there. But what I wanted to get in today is to a couple of things. So the first thing I was thinking about talking about was how we as a community could get reinforcement learning into more companies. Because right now, it doesn't have nearly the commercial success of supervised and unsupervised learning. And I think part of that could be this whole agent-human teaming, human in the loop, human on the loop, advice from agents rather than taking actions. So I would love to get your thoughts on that. And then the second part is probably even more relevant to you, where I'm thinking about agents and in general, machine learning shouldn't be learning from scratch. We should always be trying to use external knowledge. And that can be controversial. So I was going to walk you through a few of the ways that we've been doing it and why I think it's a good idea. Now, all of that said, I've been giving, because of COVID, I've been able to give talks in India, around Canada, now in the UK, and I really enjoy giving talks. But it's much more fun if you do interrupt with questions or ideas or challenges. You know, if you want to unmute at any time or turn on your video and yell at something, or if you just want to drop it into the chat, all of that is fine. I'm really happy to take this talk in any direction that you think will be most useful to you. Okay, so then I'm going to dive in. I'm not going to give the this is reinforcement learning, this is an agent, this is a state, but I did want to do just a little bit of level setting on reinforcement learning. So when I've been going to companies, I've been saying how, you know, AI has been around since the 1950s, and now the saying AI is the new electricity from Andrew Ng. Like if you're a company and you're not using AI, you might be in trouble. Now, Alberta is a huge oil producing province. So here, data is the new oil. And when you think about supervised learning, it's not all that hard to explain. So there's this recent book, Prediction Machines, which is targeted more to business audience, where they're saying, what if you could predict anything with perfect accuracy? How would that change your business? And you can get that's fairly easy to wrap your head around, right? Because if you could make perfect predictions about what your customers were going to need next week, then dude, ship it to them now, and you will not only make a lot more money, but your customers would be super happy. So we really haven't seen that kind of benefit from reinforcement learning. So part of it is, I think it can be hard to get people to really kind of wrap their heads around reinforcement learning, right? Because normally when you think of machine learning, you think of a data set. How good is my data set? How big is my data set? Is it clean? And now with RL, you've got this whole, well, I've got the agent who interacts with the world. The agent's never told right or wrong. It just tries to maximize this reward. So like the score in a video game. And, it has to usually get its own data by interacting with the environment. And I've been doing RL since 2003. And I still get taken aback when I try to explain this to someone. They're like, wait, that doesn't make any sense. And it's not because it's necessarily a super easy concept. It's just that I've been doing it for so many years. It's harder for me to see where people get hung up. And it is clear, like after I've been talking with a company for half an hour, and then they'll say, oh, well, we don't have a simulator. And no, we don't have any data about how an agent connected environment. Is that a problem? Yes, that could be a problem. So part of this is reinforcement learning geeks like me learning to better talk with companies. And we've got things like exploring versus exploiting, where you've got to convince business people that, well, we want our agents to do things that they don't necessarily think is the best thing, otherwise they won't improve. And trying to get the companies to, okay, well, sure, I could just try to replicate what a person is doing, maybe make it a little bit better. But the real thing that's hard to do is say, we've got this fundamentally different technology, this sequential decision process. Let's find a way to do something new that you cannot do with your current technology. And really thinking outside the box demands that either the RL person is embedded in the company and really understands their challenges, or there's a collaboration where the business people start to get a sense of what a sequential decision process is. So when we, and part of this pitch is, I actually talked to a bunch of recent MBA graduates, business majors, and business degree people. And I asked, so how many people think machine learning is important for future businesses? And of course, they all agreed. Everyone agrees that machine learning is important. And then you say, okay, well, where is RL successful? It's like, well, we're really good at video games. And that gets me excited, looking at StarCraft and Dota. But that's not necessarily a good sell to businesses. And they have trouble seeing how their challenges could fit into this RL framework, let alone how an agent could help them accomplish something. So maybe they understand how an agent could beat a person, but then the idea of an agent and a person working together, that's harder to explain. So one of the things I've been trying to do is come up with more real world examples. So right now I'm actually working with a few other people at Oxford to try to write a more reinforcement learning for the real world. So something that's a little more accessible than Sutton and Bartow, maybe fewer equations, fewer proofs, but is more than just RL for dummies. So kind of that in between. And part of that is being able to show some real examples. So going in and talking about how you might use machine learning for portfolio optimization and risk management, or how you could use it for pickup and drop off, and how RL has been used by Didi. Thinking about traffic light adaption. People in, I want to say in India right now, have deployed RL on stoplights to try to get better traffic flow. So we do have a lot of these examples, but we need to talk them up. And part of what I've been trying to do is go around to say, RL is mature. Companies should know about where it could be useful. And again, I think part of that's education, but part of that is also trying to figure out how to de-risk things and get humans, subject matter experts more involved. So I'll go more into that in the second part of the talk. But this is kind of where my head has been, and at a combination of, well, we want to make reinforcement learning better and faster, but we also want to take what we have right now and do a better job of getting it out of video games, out of academic labs, and into companies. Because if it's very easy for an academic like me to get wrapped up in a problem that I find exciting and is not useful to anyone. So I try to bias myself towards more real world problems. And so just to kind of summarize, the reinforcement learning is great. You can improve performance in these sequential decision tasks with relatively little data. You don't need to do tons of programming. Maybe you can discover novel solutions. And one of the big ones, when it applies, is handling non-stationarity. So if you go to a company, for instance, that has hundreds of robots in a warehouse, and over time, the actuators on some of those robots get a little wonky. And if every time one of the robots started veering to the left instead of going straight, if you had to pull it out of the factory and fix it, that's not going to be nearly as good as if you're able to adapt online to changes in the field so that you can keep these robots running all the time. So depending on the situation you're in, RL can have lots of different benefits. Yeah, I think I basically said all that already. Okay, so that was kind of my just whirlwind background on reinforcement learning to kind of level set. Then I was going to jump into kind of what I see as some of the challenges of taking this technology out of the lab and putting it in the world. And unfortunately, I have more questions than answers. So that's one of the things I'd love to get feedback from you guys. And then the third part will be how we could better learn from people, learn from other agents in order to make RL more applicable. But this is a great place for me to take a sip of water and ask for explicit questions or comments, either via voice or chat.
And everybody feel free to just speak up. No need to raise hands.
I have a question. We'll see where this goes. So I was at an RL panel at NeurIPS where someone mentioned that GPT-3 was very successful for NLP because it covered a lot of domains. You could get it to do lots of different things. You could interact with it without having to wait for it to retrain. So it showed the power of machine learning, and it was kind of a breakthrough moment in the engagement with machine learning from a non-machine learning audience. Do you think that getting RL agents to interact with people could have a similar effect, because it's easier to, like, that interaction is more meaningful than just saying, we've got some great results by replacing some old handwritten rule with a machine learning agent, and it's 20% better or something. Is that a motivation for kind of some of the direction of your work, or is it something else?
That hasn't been a motivation, but I really like that story. So in some settings, if you can go to a domain expert and said, by the way, RL could give you a 2% improvement, they're going to drop what they're doing and talk to you. It depends how important that 2% improvement is. But you're right. In general, first of all, there's the tech side. So if you want to get started, if you want to understand machine learning, you can download SciPy or download Weka and play around with some data. If you want to get your hands into reinforcement learning, now you can download OpenAI Gym and get environments and agents, but that's relatively recent, right? It used to be you kind of needed a bunch of different moving parts before you could even start to play with it. So that's from the technology side. Then from the user side, I think that's a great point. So if I had So for instance, one of the things we're talking about for future work is getting RL agents to teach people to play video games or teach people to play games. So if I could say, come to our website and I'm going to teach you how to do this, then people might find that intriguing. Or at the same time, if you say, we've got a learning agent, why don't you come to our website and teach it how to do what you want it to do? Then the same thing, that people could say, wow, I didn't realize I could teach a robot dog to do backflips. And that would be another way of gaining mind share for this technology.
I guess the challenge there is that RL can be very general. It's like there you said, you can teach the agent to do something, where that something could be basically anything. And we may need different models for different cases. And that's, I mean, okay, like language is also a challenge, but language is kind of one medium, whereas RL works in several media. And, maybe I'm a bit biased, but
yeah. Well, and if you haven't seen it, you should check for there is a talk on Tuesday at NeurIPS about the pretty surprising anti-Muslim bias in GPT-3, which they had acknowledged earlier, that based on the different religions, GPT-3 has different biases. But that's at least something that, at least in the agents I train, I don't have to worry about yet. But I think that's a reminder that data bias is something we all need to be thinking about, whether it applies to us right now or does in the future.
Yeah, that's true.
So at the beginning, you mentioned that when talking to businesses, you noted that talking in decision-making terms is a bit strange to them, or they're simply unfamiliar with reinforcement learning terminology. Because I would thought that businesses would be, or at least people simply, would be more familiar in thinking in terms of decision-making, rather predictions that you get from supervised learning, for example.
I think part of it depends on the context too. So if you're talking to a chemical manufacturer, or you're talking to and people of engineering training who understand PIDs, then I think you're in better shape. But when you're talking with someone who's more of a business side, and they're just trying to figure out, well, do I want to make more or less widgets next semester, quarter? That they're not going to have the same mindset where they're thinking of controlling a plant. Or if they're thinking about a plant, then they might be just stuck in that frame set and not thinking about other things that the agents can do. So for instance, teaching a person, that's a sequential decision task, or making stock trades. That may just not be something they initially think of. At least that's what I found, and it could just be because I'm bad at explaining RL. But I think a few people have found it challenging to go into companies and try to, well, and I'll talk a little bit about this, but try to explain what reinforcement learning is, and then try to find good applications for it.
Right. Okay. Thanks.
Just one comment following up on what Ian suggested. So I think one of the challenges in reinforcement learning is that there is a big imbalance in the problem formulation itself. Because on one side, you are having maximum generality, right? You don't know anything about the environment and you can learn to control. But on the other hand, you are focusing on a very narrow task, which is for maximizing the long-term cost or the average cost. And this is only for a single task, right? So when this makes sense is for very specific problems in the real world, like a traffic light signal or a chemical process or controlling a plane or something like that. But it turns out that in those particular problems, you typically know a lot about the environment. So you should use all this information, but then we are getting a little bit out of the reinforcement learning paradigm, or maybe not. We are starting doing more like system identification and stochastic optimal control. And that's the thing. So reinforcement learning is promising something, or at least it hints or points towards that way. But on the other hand, it's incapable of doing continuous learning, at least as it is defined in the problem formulation. We need to extend the paradigm in order to actually fulfill the promise of a robot, a real artificial intelligence agent or something like that, more general purpose.
Well, and part of it too is it's a spectrum of how you're thinking about RL. Because on one side, an RL purist will be like, yes, I want my robot to learn how to do everything and anything, and I shouldn't need to tell it anything. On the other hand, you could say, well, I've got this well-defined problem I know about. I know how to do most of it. I just want to use reinforcement learning to help tune these hyperparameters. And that's a completely legitimate use of RL. And what I'll talk about in the third part of this talk is something kind of in between, where I'm saying RL is a great framework. It's very general, but we want to add, so for instance, adding training wheels so that it can't go off the rails, adding human knowledge, subject matter expert knowledge, so that we can leverage that. It doesn't make sense for an RL agent to learn from scratch if we've got that knowledge available.
Makes sense. Thank you.
All right, I think I'm going to go ahead. Last call. Okay. So we talking about reinforcement learning now, as we already started to mention, what are some of the weaknesses? Well, the agent's going to maximize whatever reward you give it, whether it's what you want or not. Can require lots of compute. And if you're not in simulation, then it can have a real world cost. Solutions are often black box. So that's going to hinder if you want, hypothesis is that if an agent and human are working together, if the human better understands the agent, seems like they should work better together. And again, reinforcement learning performance can be very poor. So, okay, let's zoom into that last one first. So when I'm thinking about reinforcement learning, we have to think about exploration and what are the consequences of exploration. So if you do the wrong thing and the car runs into a tree, that's not acceptable. So thinking about how we could use a human or human sets of rules, or what I'll go into the third part of the talk is different ways we could use humans to bias the initial performance to help us find good solutions. But it's absolutely the case where you can put extra constraints on the reinforcement learning agent so it doesn't do anything that's too harmful. So that's going to go back to safety. So there's the initial performance. There's also the idea of batch and offline training. So if you don't have a simulator, you don't have the ability to interact with the real world, maybe you could just use an existing data set. So we see this a lot in healthcare, right? Trying to come up with a good schedule for medicine or procedures, looking at what a bunch of people have done, and then try to figure out, can I tweak what the doctors have been doing to improve things? And how sure am I that this improvement is statistically significant? So there's a bunch of different ways to do that. There's also the idea of using supervised learning. So let's say you've got this PID that's controlling an arm, and then you could use that PID to generate a bunch of data for you. And this is a well-studied problem in learning from demonstration where, so if you were watching someone driving, you got a bunch of data from their driving, then all of a sudden you make one small mistake. Now the agent is no longer in the middle of the road. The agent never saw any data from where the expert human was recovering because the expert human never messed up. So now what do you do? Well, there are ways you can get around that, ask for more data, have a safe controller take over, but that's one of the problems with trying to use supervised learning directly for these sequential decision tasks. Another thing we constantly run into is that there's going to be a limited number of samples. So for instance, if you are doing trading in the stock market and you are making real trades, if you initially start off poor, you're going to lose your money and then you won't be able to trade anymore. If you have a robot, you can only use that robot for so long before it breaks down. If you've got a simulator, maybe you've got 10 machines, you can run 10 in parallel, but your compute probably isn't unlimited. So we've got to figure out how we can be more sample efficient. And then there's the safety constraints. So I could have an agent learning to maximize points in Atari, but it doesn't really enforce what not to do. So if I an agent will generally prefer a higher expected performance, even if the variance is higher. So even if it's unlikely you will bankrupt the person by trading stocks for them, we probably don't want that to happen. So maybe we should accept a lower expected reward and actually account for that risk. So coming up with identifying critical states that we want to avoid and making sure that our agent can avoid or recover them from them. So one of the ways we did this in our own work was to use an action filter to figure out, okay, I know when some actions are unacceptable. Yes, the agent could learn that, but if I already know that, let me just hand code it. And this also relates back to human on the loop. So figuring out where an agent and a human could work together. In this case, thinking about, well, it's really the humans who's in control and the agent is making decisions. But then I believe that was kind of the way that Uber and their self-driving car were thinking about things, where we've got a driver who's in charge of the car is just driving, and then the human takes over when it needs to. And as we saw, about a year ago, that doesn't always work. So then there's the reward function. So in reinforcement learning, you can devise a very general reward, like go win the game. And that can be very hard. Instead, you often add in extra shaping rewards. So here's an example from OpenAI where this boat is getting extra rewards every time it hits these green buoys. So in this case, it's found a reward cycle where the best behavior is to just keep collecting these buoys, not to win the game. So this is where, we again go back to humans. So thinking about what is the right reward to define. Can we do elicitation? Can we look at user preferences? I really think of this as an iterative process where you're going to define a reward function, you're going to define an MDP, you come up with behaviors, and then have to go back to the experts and say, is this actually doing what you want? Because it's entirely possible the agent is going to do something you didn't expect. It could be amazing. It could be a great new solution, or it could be because there's a bug in your simulator, or you didn't specify the reward correctly, for instance. We've also done a little bit of work on shaping rewards. So thinking about how an expert could provide these rewards and not change the optimal policy. So again, a lot of problems don't have a single objective. So if I'm trying to get to work quickly, I probably want to have some trade-off between safety, time, and fuel efficiency. And there's not really necessarily a agreed way to do that optimally. One of the things you can do is come up with this kind of Pareto front, where then a person could choose from the non-dominated policies. And the person could choose, how do I want to, today, right now, trade off fuel efficiency with time? And that's something where the agent really can't come up with a right answer, because that completely depends on the user. And I mentioned before, that explainability was important. So explainability can be really useful for the nerds for helping us debug these things. But I think it's also going to be really important as we go through getting user adoption. And this is both from customers, the individual users, and as well as the business. If I go to you and say, please deploy my agent, it'll make you a lot of money, and they ask you, and your boss asks you, well, how does it work? And you just say, deep neural network. Depending on who your boss is, that's probably not going to be very convincing. And of course, the more explainable it is, the more you can learn from it. So as we deploy these agents, hopefully they are finding out new things that the business can exploit, that they can find some new behavior, find some new ways of doing business that they hadn't noticed before.
I have a question on explainability. That's okay. So I read a paper recently that suggested, admittedly in one specific case, the more explainable their model was, the worse the human AI team did in general, because the human trusted the model more and ended up just saying what the model was saying because it gave an explanation, even when it was unsure, even when the model had some uncertainty, because ultimately it gives the most likely outcome in its view. They just took it every time. Whereas if you just gave sort of a probability distribution, then the human would often provide its own view rather than just take the model's view. And in some cases, there's a trade-off between explainability and the overall performance of your human AI team. I wonder if that's something you'd come across or had a view on.
So I would actually argue that's just not a great way to do explainability. Anytime you're making a decision, you better not just say why, but how confident you are. So there was another study where so they had this classifier that was helping to do things, and it wasn't perfect. But the users got a sense of where the classifier was right or not. So they could do really well. Then what they did is they changed the classifier so that it was more accurate, but now on different samples. So now, even though the classifier is more accurate, the user's model of the classifier is now broken. And because of that, the team does worse. So I think your core point that you really need to think about the team performance rather than just the agent is a really critical one. And I think explainability is part of that, accuracy is part of that, or confidence can be part of that. But it's really, you got to think about the whole team, not just the agent.
I think it feeds into something you were saying before you started the presentation about your course wanting to incorporate people like psychologists and people from different areas. And I think that in the way you present and interact with people and get stuff from people is an area where that's more relevant or more significant. So cool.
Yeah, and I mean, to be cynical, there's different kinds of trust, right? What we were just talking about is, can the user figure out when to really engage with this tool? A more cynical one would be, can I get the consumer to buy my product? And that's a very different relationship.
Yeah. Thanks.
Yeah. Any other questions or comments before I go on? Okay, then another thing I wanted to point out is, in real world reinforcement learning, you have some amount of compute and you have a deadline. And now, how do you choose which algorithm to run? Do I want to use SAC or PPO? Okay, let's use SAC. Well, then what neural architecture do I want? How many layers do I want? What activation functions do I want? Hyperparameter. That was supposed to be hyperparameter search. I've got all of these different knobs I can tune. How much compute do I spend on training them? How long should I let an algorithm run? Am I really sure it's converged? Do I want to let one algorithm run for 5 days, or should I let 5 trials run for 1 day each? All of these are practical questions in terms of how do I get my machine learning model deployed. And all of this goes back to human intuition, because we don't have great ways of doing this. So for instance, there are very principled Bayesian optimization ways for doing neural architecture search. But I believe all of those still have some caveats. And even then, that could be ignoring all of these other different search dimensions. And then, just as an aside, as an academic, you might spend, years tuning this, and then you say, oh yeah, and my agent was able to learn in just 2 days. Like, well, sure, but that's discounting the sunk cost. Here's a general thing I've been thinking about, just how do you do RL if your company doesn't have an RL expert? How do you identify good problems? How do you upskill? If you're going to a company, this is probably more relevant to you, how do you explain RL and how do you find a good problem? So these are the kinds of things I've been thinking about, and I don't have good answers. But then even once you've identified that problem, so okay, the company wants you to optimize this plant. Then how do you de-risk? How can you say, yes, I'm pretty sure reinforcement learning is going to work, or the state action space is just too big. It's not going to work. And oh, by the way, how do you figure out? Yes, I think I can get a 1% improvement versus a 500% improvement. Is there a simulator? How expensive is exploration? All of these things are questions that, as we engage with companies, we need to be able to better understand. So, kind of in summary, there's a bunch of things that makes an RL task hard, and we have some ideas about that, but we still don't have a good way of saying, this task I can solve in a week. This task is going to take me 2 months of research time. And similarly, we still don't have a good way of going to a company and saying this is a good task versus this is a bad task. So one of the things that we often forget about are second order effects. So if you can say, well, we're the first company to be using AI in this sector, that actually could be worth quite a bit. So there's all of these technical and non-technical things. So the final slide in this section was I wanted to present one thing that Amy is working on right now, which I thought these kind of came together. So ISL is an Edmonton tech startup. And here there is a water treatment plant. So water is actually coming in from the North Saskatchewan. The sensors are looking at it, and then we can take actions over time where we change the chemicals, we do a backwash cleaning, that kind of stuff. And here the rewards are some combination of environmental and fiscal. So right now we're in the early stages of this, but this is the kind of example where if we can show that we actually can get both environmental and fiscal benefits, and then we can take this model and bring it to other water treatment plants. Like that's going to be a big win. I mean, in terms of money for the company, but also for the environment. So I was really excited that Adam and Martha White were able to identify this particular problem. And I would love to see reinforcement learning doing more of this kind of thing. So the final section of my talk is, okay, how do we actually incorporate external knowledge? And I'm going to argue that that's going to be a big part of getting reinforcement learning into the real world. But I'm also going to pause here for a second. What I've been thinking about over the past 10 years or so is I don't want a single agent. In general, there's going to be some existing knowledge. So if I want my agent to learn, if there's a human who knows something, that human better be helping him. Or if I've already got an existing agent or a program, that better be helping the new agent. And this is going back now to the title of the talk, where I prefer even to fail with honor than win by cheating. And if you haven't read it, Rich Sutton's The Bitter Lesson is pretty interesting. That generated quite a bit of commentary. And one of my interpretations of Rich's point is every time we've injected human knowledge and bias, it's kind of been a waste of time. It's led us down the wrong path. And as compute got better and as our algorithms got better, we didn't need it. So let me start by saying this kind of cheating coming from other external knowledge comes in a lot of different ways. So one of them is transfer learning. So just taking the brain of one agent and putting it into another. That's a way you could speed up. But there's many cases where you don't have access to the agent's brains. And there's some drawbacks there. One thing a trained agent could do is design a curriculum. So that's something a trained agent or a human could do. So kind of lead the agent through a sequence of tasks. And in some cases, the agents can learn that sequence faster than if they just trained on the very hard thing. So if you haven't heard of that curriculum learning idea before, it's been better studied in supervised learning, but it's been gaining followers in reinforcement learning. So there is a survey out recently that I happen to like for some reason that I think is pretty good. So if you're interested in curriculum learning, I could recommend that. We already mentioned off-policy learning. So if I've got a bunch of data sitting around, I should use it. And this data could come from a human. It could come from an existing program. It could come from a PID. So one of the things we've been thinking about is, if I'm learning a policy, how do I decide I've got enough data? Now I trust my policy well enough to start using it. Or let's say, going back to the stock market trading, let's say you're paying your broker to trade for you. And the broker takes some commission. At some point, if you had enough data, it seems like you should be able to say, even if I'm only I'm 40% confident that my policy is good as my broker, if the broker was charging enough, it still might be worth making that switch. So there it comes back to a risk total utility kind of thing. Okay, so then my general argument is we can get data, we can get advice from people or programs, but the data is probably going to be suboptimal, and we don't just want to focus on nerds. So a lot of computer scientists work with real people, and that means going down the hall to get another computer scientist to machine learning. That's not going to necessarily generalize, but we can go and get advice or help from subject matter experts or lay people. So we could get people to actually teleoperate the system for us, like teleoperate the robot, or give us some action advice, or some feedback, or preferences. So even if it's just, I've tweaked my reinforcement learning reward, and I've come up with 3 agents that I think are doing pretty well. Let me go to a subject matter expert, and they can tell me which one is actually better and why. That helps me, again, redefine the problem, tweak what I'm trying to do, and get better results over time. So let's see, given the time, I think I'm going to skip this and just say, this is the kind of result that we've been getting. So this is 10 years old now. And here's an example where we could learn using normal reinforcement learning, or we could learn with a method that uses human demonstrations. And you can see, okay, the final reward is better. The area under the curve is better. But, well, is this actually an improvement? Well, one way you could measure that is say, well, how long does it take to get to a certain performance? Well, if I really cared about getting to 14, I could go now from 14 hours to 8 hours. So that could be useful. And the kicker is this is with only 3 minutes of human time. So in some settings, getting just a small amount of human performance can provide huge benefits. And right now we're thinking about, where do we want that advice? Do we want it usually at the very beginning? Maybe we want it more towards the end, where I was talking about looking at those different 3 policies and deciding which one is best. And the last thing I'll mention is we could have I've been thinking a lot about a student-teacher framework. So the student is going to be an RL agent, and the teacher could be a person, or it could be an agent. And you could say, well, the teacher knows the domain. The teacher should be the one to interrupt the agent and help it. Or you could say, well, the student knows what it's confused about. The student should be the one to ask for help. And we've shown that both can work in certain settings. And in fact, combining them in some cases can be even better. And this is one of the places where I think explainability is going to help. So trying to figure out, if I can use explainability if I can better understand the agent, understand how the agent will act, then hopefully I can provide the agent better advice. And I really think explainability is going to be critical for human agent teaming, because if you cannot anticipate what your teammate is going to do, that you're not going to trust them and you're not going to work as well. Let's see, skip ahead. The last thing I'll mention here is we're also looking a little more theoretical, looking at value of information methods. So for instance, you could say, if I'm in a multi-armed bandit setting, let's suppose I have an oracle and the oracle costs something. Should I pull the arm with the highest expected payout, or should I pay the oracle and then pull the best arm? And this is going to depend on what the teacher is telling me, or if the teacher is not an oracle, what if they're only 90% accurate? You know, so if it's a matter of, well, I know Bob's really busy, but Bob is right 75% of the time, should I bug him now or not? And if we can better reason about those types of questions, then we should be able to get better agent-human interaction, because we do not want to waste humans' time, but we also don't want to give up lots of performance if we could just get a little bit of help from a human. So to kind of wrap things up, I mentioned this a little bit. One of the future directions we're going in right now is trying to help a human. So for instance, if you had a simulator and you were training in the military or training in education, can you better teach people by proactively providing advice and support? And do you want to provide hints, or maybe partial solutions or full solutions? There's one of the failure modes here is when I was in grade school, I was trying to learn to play chess. And what I would do is on every turn, I would just click the button and say, please tell me what to do next. So I got very good at following exactly what the chess program thought I should do, but it didn't help me learn how to play chess at all. So if you are interested in human RL interaction, we do have this class that just wrapped up, which I still need to finish grading for. The best part of teaching, doing grades. And I do want to give another shout out to Ian for coming and talking to my class. I really appreciate that. The students really liked his talk. It was fun seeing, again, going out of video games and thinking about real world problems. But if you were interested in video games, we are releasing this new framework that lets humans interact with Atari games over the internet and OpenAI Gym games. So if you wanted to give agents demonstrations or feedback or point out wrong actions, I'm hoping that this framework will help get more people interested in human AI interaction and human RL teaming. So just to finish, I don't think getting this kind of external help is cheating. I think working with humans, even if the end goal is for an autonomous agent to solve the problem, I think working with humans is critical. Yes, we could work on building better algorithms. Yes, this is biasing our agents. But right now, I want to solve hard problems. And there are very smart people who are working on getting better algorithms, and I'm doing a little bit on that too. But I want to know what we can do today if we have the right kinds of knowledge from people or other programs. So I think there's a ton of open, interesting questions here, and that can potentially be addressed in the short term, not the 10 to 15 year timeline. So with that, I'll stop talking. And as always, I'm happy to talk now. I believe I'll be meeting with some of you tomorrow. And if you'd like to find out more, you could go to my lab's website, the IRL lab, irll.ca. Thank you.
Thank you, Matt. That was a really wonderful overview of, well, mostly challenges in applying reinforcement learning to real-world settings. Well, we have some of those experiences as well. I think we can sympathize. Definitely the reinforcement learning team here can recognize quite a few issues here.